Hello, OSA Advanced Photonic Congress. My name is Marco, and I'll be present here to you the one-step synthesis of fluorescent carbon dots from two widely available natural sources. This work was developed at the Laboratory of Photonic Materials and Devices of the University of Campinas in Brazil. So, what are the carbon dots? These are nanoparticles constituted by carbon nucleus covered by functionalized surface groups like carboxylic acids, alcohols, or amines, forming, as you can see here, this corona layer, this layer of oxidated surface, in a crystalline core, crystalline or amorphous carbon core, in which the carbons are linked by a mix of sp2 and sp3 bonds. These are low-cost materials, environmentally safe, and biocompatible, so they have a lot of potential for replacing the inorganic quantum dots considered the superior fluorescent emitters, but that are very toxic. So the most important photonic property of these dots is the luminescence, where the atoms are stimulated by an external source of energy that takes the atomic electrons to a higher electronic state, and the return to the fundamental energetic states leads to the consequent photon emission. So the synthesis from organic compounds rich in nitrogen and carboxylic acids results in CDs rich in carboxylic or amine surface groups that are the major contributors for the fluorescence. If you choose properly the reactants, if the nitrogen or oxygen and other heteroatoms like bromine source, you can obtain very different compounds. For example, in the synthesis, the authors present the blue, red, and even the pure white light emission. But how this emission takes place, the mechanism of the CDs is still under debate. The main hypotheses are the generation and recombination of electron hole pairs, the quantum confinement effect, especially for the crystalline structures like the graphene quantum dots, and the detected state emission. The CDs usually exhibit a strong absorption band in the UV around 230 nanometers that is ascribed to the PP antibonding transition of the sp2 carbons of the core. And tail expanding over the visible that is usually attributed to the NP antibonding transition of the peripheral functional groups that bear electron lone pairs. One very interesting property of these dots is the excitation wavelength dependent emission, as you can see in this picture. When changing the excitation, depending on the dots, you may have very different colors, very different emissions, even for the naked eye. And this wavelength emission, dependent emission, depends on the surface effects, on the elements that are doped in the dots, the particles diameters, and also the solvent neighboring part of the particles, the solvatochromic effect. And how do we obtain these dots? A very interesting approach is the microwave-assisted synthesis that does not require multiple reaction steps, promotes higher energy reaction yields under milder conditions with lower energy consumption, providing a fast, scalable, eco-friendly, and cost-effective process for the production of the dots. So the carbon dots may be obtained from natural sources in very eco-friendly processes. For natural sources, diameters from less than 10 nanometers ranging to up to 15 nanometers are reported for the synthesis. This work that we are presenting here today is an adaptation of the method that we already reported for the synthesis using sugarcane syrup. That's a very widely available source in Brazil. So in this case, we use the ultra high temperature UHT milk and the orange juice. We heat it in a microwave oven for 2 cycles of 1 minute each cycle, opening the oven for relieving the pressure and obtaining a brown, dark solid that was redispersed in water using the ultrasound bath and filtrated in cotton or filtration paper for removing the larger particles. And then the most important purification process, that is the centrifugation using membranes with molecular weight cutoff of 3,000 Daltons. So after this process, a yellowish solution, orange solution, containing the functionalized dots is obtained. But it's important To note that the hydrothermal treatment, in fact, was already used for obtaining these dots, but with very drastic conditions and higher energy consumed. For example, for orange juice was used the treatment of 120 degrees for 2.5 hours, or for milk 180 degrees for 2.0 hours. There are drastic conditions capable of providing dots with crystalline structures. The approach of this work uses a faster of only 2 minutes and more energetically efficient microwave assisted process for obtaining the dots. The most important property that allows the synthesis is that both raw materials are rich in organic compounds, organic acids, for example, the ascorbic acid and the citric acid with plenty of carboxylic groups in the case of orange juice, and also fructose that provides oxygen atoms. And milk contains lactic acids and lactose that provide lots of oxygen, and also proteins, example casein, with lots of nitrogen atoms. So the presence of the heteroatoms, the nitrogen and the oxygen, provides excellent optical properties. So we obtain a one-step synthesis with no need for other reactants. We characterize the particles for atomic force microscope. And it's important to cite here that besides the availability of other characterization techniques, for example, the transmission electron microscope, this one may be not recommended for this kind of synthesis because the particles may aggregate under the high vacuum, so you won't obtain exactly the particles that you obtained. So the AFM showed for the orange juice derived particles, semi-spherical particles with diameters ranging from 2 to 5 nanometers. These are dimensions consistent with the green fluorescence. It's important to notice here that you only should look at the z-axis which presents a high precision of 0.002 nanometers, because due to the very lower diameters, uh, there may be tip-induced distortions on the XY plane that are too amplified due to the low diameters. In the case of the milk, you don't observe such higher distortions on the XY plane because the particles are higher of 53 nanometers, and it's very clear the semi-spherical shape. So these diameters are consistent with previous reports of CDs, and these bigger diameters obtained from milk suggest a higher organic content that we already expect since there are lots of proteins, for example, casein. So it's possible to optimize the heating time for each one of the sources, obtaining lower diameters and lower dimensional distributions. We physicochemically characterize the particles by Fourier transform infrared spectroscopy and detect the presence of alcohols, carboxylic acids, amines, aldehydes, and ketones. So the aromatic core uh, gives us the CC stretching here, and also there is the presence of OH and NH in the case of the milk, and apparently a more intense OH signal for the carboxylic in the case of the orange juice. It's probably a consequence of the usually more acid content of the orange juice that contains the citric and the ascorbic acid. Also, there are the carboxylic acid anhydrides, the carbonyl, and other groups. These functional groups bear the electron lone pairs, so they contribute to the fluorescence and make these nanoparticles polar, and more important, water soluble. These particles are really hygroscopic, so they may be also functionalized through the covalent attachment only in these groups. When we observe the aqueous dispersions, we see an orange aspect for the orange juice-derived CDs and a pale yellow aspect for the UHT milk. And when we irradiate it with 254 nanometer UV light, we observe this green-blue fluorescence, apparently more stronger for the orange juice. And it's important to cite also that there is a long-term stability The suspensions are stored under room atmosphere and 10 degrees for about 6 months, and no observable change of aspect, color, or fluorescence was detected. They characterized the absorption spectrum and detected the maximum absorption under about 208 nanometers, that is the PP antibound transition of the sp2 carbons of the core, and there's this shoulder about 300 to 360 nanometers that concerns the NP antibonding transitions involving the electron pairs of the functional groups. You may observe that about 350, 360 to 400, there's a great decrease on the absorbance. So the emitter light is low absorbing here. We characterize the particles regarding their fluorescence spectrum, and as you can see for the orange juice-derived carbon dots, there's when irradiated under 350 nanometers, you observe the maximum fluorescence about 426 nanometers, that's the violet, and the emission spectrum extends over the visible with an intensity decrease as it takes redshift. We also characterize the UHT nude fluorescence, and apparently the shape of the cubes are very similar, but as you can see, there's a great decrease of intensity. We could observe it because the two samples were characterized simultaneously in the same equipment. But as you can see, the maximum emission occurs very similar under 425 nanometers violet, but under an irradiation a bit lower, that is 30 nanometers. And again, the spectrum extends over the visible with redshift. Intensity decreases the redshift. The lower intensity are possibly due to the higher diameters of the particles, but there may be also an effect of the lower carboxylic content. These materials present a lot of potential applications, for example, low-cost environmentally safe fluorescent inks, since the group of Zhu showed the possibility of using aqueous dispersions of CDs as low-toxin fluorescent inks. Several authors have been testing dispersions and composites where CDs are put into polymer matrix. For example, recently it was shown that the occlusion into solid or even polyvinyl alcohol matrix allows the obtention of phosphorescence or even delayed fluorescence. These UV active markers present lots of applications, for example, protection of documents, anti-counterfeiting, proof of ownership, quality control, industrial process, or any condition where someone needs to invisibly mark things for future identification. So, we showed here a fast and green methodology for the obtention of fluorescent nanoparticles with potential applications on fluorescent inks, soft electronics, biomedicine, photocatalysis, and renewable energy source. This synthesis is only renewable and low-cost source, obtaining diameters from up to 5 nanometers to 53 nanometers, and fluorescence with excitation-dependent behavior. The organic nanoparticles are rich in functional groups bearing electron lone pairs, and the heating time is the main process parameter and may be optimized for each raw material. Again, the synthesis is possible under microwave due to the presence of the electrons of the sources. So thank you for the attention. Thank you also for the possibility of presenting this work. Thank you the São Paulo Research Foundation for funding this work, the laboratory equip of Professor Marisa Beppo for helping us with the fluorescence characterization, and the National Technology Lab for the AFM. Bye, everybody.